Alrighty, so now that we're recording, I almost forgot, and that would have been catastrophic. Boop! One thing that I forgot to add to yesterday's binomial coefficient stuff, right here at the top. I'm going to add one more thing. N choose n equals 1. Because remember what the choose function tells us? The choose function says, how many different ways can you build a smaller group out of a larger group? Right in front of me, I have a group of 4 guys. How many ways could I build a team of 4 from these 4 people? One way. So how many different ways could I choose? None of them? One way. I just did it. I chose none of them. How many different ways could I choose? All of them. One way. There, I'm choosing all of them. Okay. And it's important that you understand these two concepts, that any number choose 0 is always 1, and any number choose itself is always 1.
Oh, that makes you explain, like when I asked you about the n choose 0 yesterday, like the way you just explained it right now. Like,
that helped out?
Yeah,
Perfect.
you said, like, how many times you can pick out of this.
Yeah, how many ways can I pick none of you? There's only one way. Okay, cool. Well, I'm glad that worked. That's, but it could be any number. And that's why that number was 1. It could be 17, choose 17, 1. Okay. Now, yesterday I talked to you about how to use your calculator to find these things, not necessarily what they are. This lesson is actually about expanding binomials to any power we want. A binomial is anything that has 2 structures inside it like this. We can raise this to any whole positive power we want. And, so I could ask you to do stuff like this. You don't need to write this, but let's just say I don't like you, and I make you do this. I could say, what is the 5th term in this expansion? And if you didn't know how to do what we're going to learn how to do today, you'd be forced to FOIL 8 frigging times and track down all the like terms and add them all up. And oh boy, would that suck. There's got to be a better way. And of course, there is a better way. That better way is called the binomial expansion. And the binomial expansion, one way that we can do it is using Pascal's triangle. So Pascal's triangle is a pattern that is specific at this point to expanding any binomial. It has rows. It starts at row 0. Then it goes row 1, row 2, row 3, so on and so forth. Over here, I have a very simple binomial, x plus y. Here's x plus y to the 0, a 1. X plus y to the first is just x plus y, right? But what are the coefficients? They're 1 and 1. X plus y squared simplifies to x squared plus 2xy plus y squared. 1, 2, 1. X plus y to the third. Its coefficients are 1, 3, 3, 1. 1, 3, 3, 1. And if I did x plus y to the fourth, it would have the numbers 1, 4, 6, 4, 1. If I did x plus y to the fifth, it would be 1, 5, 10, 10, 5, 1, so on and so forth. Now, this Pascal's triangle, we attribute it to the mathematician Pascal, but we have a lot of evidence to show that we've actually known about this as a human species for 8,000, 9,000 years. All the way back to the very first civilization. I'm pretty sure recently they found evidence that the ancient Sumerians, which were the first civilized humans, the first human civilization on the planet that we know of, that they had knowledge of this pattern. And this is a pattern. This isn't something you memorize. It's something you build. And in case you've never seen it before, let's see if while I'm building row 6, if you could figure out how to do it. 1, 6, 15, 20, 16, 6, 15, my apologies, 15, 6, 1. Do you see how they're built, Hunter?
Yeah, okay, so you take 2 numbers
Mm-hmm.
that are next to each other, you add them together.
There you go. The 2 numbers that are immediately above it add up to this number. So 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, so on and so forth. These numbers are called the binomial coefficients because they're the numbers that would sit in front of the expansion. Okay. Notice each one of these terms, I lost, when I get from one term to the next, I lost an x, but I picked up a y. Look at that. 3 x's, no y's. 2 x's, 1 y. 1 x, 2 y's, no x, 3 y's. Each time I move over a term, I lose an x, I gain a y. Also, look at the exponents on the variables. 3. 2 plus 1, 3. 1 plus 2, 3. Here's another 3. Each term's exponents add up to this exponent. And by the way, this exponent is the row number. So we use Pascal's triangle to do expansions of binomials when the exponent's not too big. I'll be real with you, I probably wouldn't go past row 5. This would be row 5. The second number in the row is always what row you're in. I wouldn't go past row 5 because I'm not trying to build Pascal's triangle. So essentially you start with a 1 and then you go 1, 1. And then from there on out you just add. So no, you don't have it memorized. You just know how to build it and you build it when you need it. But I typically wouldn't even bother building it past row 4. Maybe row 5. Maybe. And that's only if I was too lazy to grab a calculator. Because each one of these numbers is actually one of these numbers. This is 6 choose 2, right? We know it's 15. This number is 6 choose 0. This number is 6 choose 1. You know what? I'll write it underneath it. This one is 6 choose 2. This one's 6 choose 3. 6 choose 4. 6 choose 5. And 6 choose 6. So every entry in the row is a binomial coefficient that the choose function would have given to us if we had used our calculator. So again, Pascal's triangle is useful if you can get to it quickly, because you can get to row 4 pretty darn quick without grabbing a calculator. But past that, well, I mean, what's 5 choose 3? I don't know. Let me grab a calculator. I don't know what 5 choose 3 is. 5 choose 0, 1, 2, 3. Okay, 5 choose 3 is 10. You know what's interesting about this, though? This is term 1, choose 0. Term 2, choose 1. Term 3, choose 2. Term 4, choose 3. Term 5, choose 4. Term 6, choose 5. Term 7, choose 6. If you look at every row of Pascal's triangle, it always has one more number than the row number. And the row number is also the power of the binomial expansion. So each row has n plus 1 terms in it. That's because every binomial expansion has the power plus 1 terms in it. What is x plus y to the 6th? I don't know, but I do know that it has 7 terms. Okay? And that whole, the number we're choosing being 1 less than the term number, because this is term 2, but I'm choosing 1. This is term 4, but I'm choosing 3. That idea is going to come into play on the back. Now, Pascal's triangle shows up in a ton of different mathematics. It shows up all over the place. I mean, just in things you wouldn't even expect. Last year, or the year before, I can't remember, I ran across a pattern in calculus that was so freaking cool that I ran down the hall to Miss Bluebaum and I was like, yo, look what I just found. Essentially proving what kind of a giant nerd I am. And I was like, I just found Pascal's triangle in these derivatives. You don't know what that means. But the point is, I was like, look what I found. This is crazy. Miss Bluebaum was like, I said, have you ever seen that before? She says, no, I've never seen that before. I mean, we both recognize Pascal's triangle. And she was like, that's like you can get published. You might have just discovered something brand new. And I was like, there's no way that I'm the first mathematician to just wonder what if and found this. Here, turns out I'm not. Hundreds of years ago, like the father of modern calculus, he found it. But the point is, it's every freaking where, and it pops up everywhere. We don't know it. So other neat things about it. Other really neat things about it. I already told you row 2 shows you what row you're in. Other neat things about it. It's symmetric. So that's cool. I mean, it's pretty cool. Hold on, I see your hand up. Hold on one second. So it's symmetric on both sides. Something else that's really neat, and I didn't even notice it, a student noticed it a long time ago when I was teaching this material. First row, what's it add up to? 1. What's the next one row add up to? Then? 8. 16. Let me summarize for you. 1, 2, 4, 8, 16, 32, 64. What are these?
Doubles of 2. Squares.
Powers of 2. They are powers of 2. What power of 2? Bless you. What power of 2? Row number power of 2. Row 3 adds up to 8 because 2 to the 3rd equals 8. Row 6 adds up to 64 because 2 to the 6th is 64. Really stinking cool. It really is. So yeah, that's what's up with that. We will use Pascal's triangle to find binomial coefficients if the row number is not too large. Okay? If the row number is huge, boom. Okay? We just use a choose function on our calculator. But what if I asked you to expand something, not just give me the binomial coefficient? What you need is the binomial theorem. Oh my golly, look at that mess. It is so big. It does, you know what? It's definitely pockets full of spaghetti. That's definitely what this is, okay? Now look, I'm going to make it a little bit better for you. These two rows say exactly the same thing. One of them is showing the choose function in the stacked format. One is showing the choose function that you would see on your calculator, but they mean the same thing. Yes. Graph what? Well, I mean, if you're assuming it's a polynomial, sure. You mean if I said graph x plus 5 to the 3rd?
Oh, yeah.
It would be the same thing as if you cleaned it all up. It's the same. Can it be used to calculate numbers by hand that you never would have thought of? Yeah. But I'm not going to make you do that. Like if I said, what's 1.1 raised to the 4th power? I could use Pascal's triangle to do that by hand. Which is just kind of neat. Then we're not going to waste our time. But I am going to fix this up a little bit. Tell you what we're going to do. First, realize that these shouldn't say x plus b to the n. I'm going to say every one of them should have said a plus b to the n, because the binomial theorem is how you expand a plus b raised to the nth power. Notice, like I said before, each time you move over, you lose an x but pick up this second term. So for us, it's going to be we lose an a and pick up a b. But look here, n choose 0, exponent is an n. N choose 1, there's 1 b. N choose 2, there's 2 b's. N choose 3, there's 3 b's, so on and so forth. And these exponents, n minus 1 plus 1 adds up to n. N minus 2 plus 2 adds up to n. 1 and n minus 1 adds up to n, so on and so forth. If you want to do the expansion of a plus b to the n, term number r plus 1. So that's like term 5, term 18, term 24. Term sub r plus 1 is n choose r, a to the n minus r, b to the r. R is the number of objects you're choosing from a group of size n. This is the size of the group that you have to choose from. This is the size of the group you're choosing from it. Like 5 choose 2, here, your table of 4 guys. If I say 4 choose 3, then R would be 3. It's the size of the group you're choosing, and B would have the same power as this number down here. This just tells you which term it is in the expansion. This is the coefficient of term 1, term 2, term 3, term 4. These are the coefficients. And you see how the number on the bottom, r, is always 1 behind the term number? This is a 0 at term 1, a 1 at term 2, a 2 at term 3. R is always 1 behind the term number. So that is beneficial to us if we wanted to say, what's the 5th term in the expansion? If I say, what's the 5th term in the expansion? You go, oh, t sub 5, so r is 4. So you would put a 4 right there. So it tells you what r equals. Great. We're going to use this to expand x minus 2 to the 3rd. We are not going to do x minus 2 times x minus 2, FOIL it, and clean it up and get x squared minus 4x plus 4, and then multiply that to x minus 2 again, and all the foilings cleaning up. We're not doing that. We don't want to do that. Instead, what we're going to do is identify a, b, and n. A is x. B is negative 2. N is 3. Our binomial coefficients, which are all these choose functions, are going to be the numbers in row 3 of Pascal's triangle. Let's say you don't have Pascal's triangle memorized. No big deal. You find a tiny paper square on your paper and you go 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and the second number is the row. Ah, there it is, 1, 3, 3, 1. So I know that my binomial coefficients will be 1, 3, 3, 1. I'm going to do my binomial coefficients in orange. And I'm going to do my A and B things in blue. The first term will be 3 choose 0. You always begin your expansion with n choose 0. 1 choose 0, 2 choose 0, 3 choose 0, 4 choose 0, 5 choose 0, 6 choose 0. Yes?
Is row 0 because anything to the 0 is 1?
That's why. Row 0 has a value of 1 because anything to the 0 equals 1. So here I have 3 choose 0. A to the n minus r. A to the 3 minus 0. Oh, x to the 3 minus 0. So how many b's are there? None. But when I go to the next term, remember, the number in the bottom of the choose function is the number of b's that you have in your expansion. But if I gained a b, I lost an a. Next is 3 choose 2. Oh, that means there's going to be 2 b's. But if there's 2 b's, I've lost another a. And the last one is 3 choose 3. Every expansion begins with n choose 0 and ends with n choose n. All of them. That means I have all 3 are b's. That means I have no x's now. Anything to the 0 power equals 1. So this is 1 and this is 1. And I already know what these orange choose functions values are. They're 1, 3, 3, 1 because they represent row 3 of Pascal's triangle. So I'm going to clean it up just a little bit. It's going to give me 1 x to the 3rd. And then 3x squared times negative 2. And then 3x times 4. And then 3 choose 3 is 1. Oh, crap, I meant to do that in orange. 1, 3, 3, sorry. 1, Negative 2 to the third is negative 8. My expansion cleans up to this. X to the third minus 6x squared plus 12x minus 8. And you might have been thinking, I could have FOILed faster than that. Okay. That's only if it's a third power. What if it's the 23rd power? No, you wouldn't ever write them all out. But if I asked you for the 17th term of the 23rd expansion, you could just use this instead of finding them all. Before I move on to the next example, I need you to ask questions that you have. Plus, it's good for the video anyway. They've got to be out there somewhere. Yes, David. Oh my God, yes. We'll definitely use calculators because I'm not going to go to like row 7 of Pascal's triangle. I'm not doing that. No. The calculator cannot do it with a variable. This is just the polynomial. We'll use the calculators to find the coefficients that sit in front of these things. You'll see it in this one. You'll see what I mean by that. Yes?
Did you get negative 2 from the equation number given?
This is A and this is B. Because it's always A plus B.
Oh, okay.
So that would make B a negative 2 there.
Okay.
Where A is X and B is negative 2. And you know what's really cool? Because Pascal's triangle is symmetric, you could switch A and B and it won't change the answer.
Okay.
Because it's symmetric. You won't be in standard form, because polynomials aren't in standard form unless they count down, but the result is still the same. You would just have to put it in the right order. Yeah, Cooper, what's up?
In the formula, what is t?
T is the term number. So this is term 1, term 2, term 3, term 4. You see at term 4, it was term 3 plus 1, because the bottom number was a 3, because it's always r plus 1. So this is just which term you're looking at. Oh, I want to know what the term 2 was. Oh, term 2 made me have r was 1. That's all it is. It's just term. That's what it stands for. It's like when you do sequences. You're like, oh, that's the first term, the second term, the third term. It's all it is. More questions? Yes, Uriel. What is B? So it's just one of the two things in the parentheses. It's always an object plus another object. So here, what you're thinking of this as being is x plus negative 2. So A is x and B is the negative 2. It's just the other thing in the parentheses. Cooper? You mean, does it only work for binomials?
Yeah.
What a great question. I'm going to let you Google that. By all means, look up, not now, but look up trinomial expansion patterns. See if you can see any. Or better yet, be a huge nerd and start doing some trinomial expansions of your own and see if you see patterns. Not now. Put the phone down. Yes, there's patterns in it, but it just isn't as useful to us. Yep.
You just put that into the binomial theorem equation, right?
Boop. That right there, yeah.
Okay.
So let's do it again. This time, A is 2x. B is negative 3. N is 4. Okay, tell you what. I already have row 3 of Pascal's triangle up here. I might as well get row 4 also. 1, 4, 6, 4, 1. I mean, it was already there. Look how little effort that required me to find. So I now know my 5 binomial coefficients are 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. In all reality, you can actually skip over this first line. I don't want to skip it, though, because I'm really trying to drive home how this thing works. Right skinny. 4 choose 0. A, which is 2x, to the 4th, and no b's. But then, you got 4 choose 1. lose a 2x. Gain a negative 3. Why? What are you guys doing? 4 choose 2. Lose a 2x. Gain a negative 3. 4 choose 3. Lose a 2x. Gain a negative 3. And lastly, gonna barely fit. 4 choose 4. Think skinny thoughts, mathematics. 2x to the 0. Negative 3 to the 4th power. Eek! Suck it in, 4. You can fit. Okay. Cool. All my orange choose functions, I already know what they equal. They equal 1, 4, 6, 4, and 1. Because that's row 4 of Pascal's triangle. So let's clean it up. 1. 2 to the 4th is 16. X to the 4th is x to the 4th. Four choose 1 is 4. 2 to the 3rd is 8. X to the 3rd. Oh, times negative 3. Four choose 2 is 6. 2 squared is 4. X squared is x squared. Oh, but negative 3 squared is 9. Is it just my eyes, or is this image a little out of focus?
It is.
It's a little out of focus, right?
A little, not much.
No, wait for it. It's auto focusing.
Yeah, there we go.
Oh, that's better. That's crispy. Yes, London. Okay. Yes, Cooper.
How do we get the numbers, like what the power is?
You mean how am I getting the exponents of 4, 0, 3, 1? Because the first one, it's always n minus r. The first one is always going to be n. So look, he's not listening. He asked a question and then immediately started talking to somebody. The first one's going to be n choose 0 always. So this is n minus 0. So this is a 0. The next one's going to be n choose 1. So this is n minus 1, and that's a 1. So 4 choose 1, 4 minus 1, 1. 4 choose 2, 4 minus 2, 2. Just like that. London?
So on the next, like the one we're writing right now, would that be like 1 times 6 x to the 4?
This,
And then
we're here. 4 choose 3 is right here. This is 4 choose 0, 4 choose 1, 4 choose 2. This is 4 choose 3. So it'll be 4 times 2x. And then negative 3 to the 3rd is negative 27. And then the last one, 4 choose 4, is this 1. And I don't need to bother with 2x to the 0. I just need to know what negative 3 to the 4th power is. It's 81. How do I do that? Well, first of all, I know that an even number of negatives gets me a positive. I know that 3 times 3 is 9, and 3 times 3 is 9, and 9 times 9 is 81. Okay? That's how I did that. And now we can clean it up. And if you need to grab a calculator, that's fine. I have a 16x to the 4th minus, because look, there's a negative sign here. What is 8 times 12? 96? Then plus, let's see, 54 times 4 is 216. So on your calculator, you would just ignore the x's. You can't type those, you'll confuse it. But you could do 6 times 4 times 9. Minus 4 times 2 times 27. Which is actually 4 times 54 again, so 216 again. And then there's an 81 at the end. Ta-da. Yes, Cooper?
It's like the fact it's 216 twice, like part of it.
Nope, that is coincidental and actually kind of cool. 100% coincidental. Yes, ma'am, Ariana. So if one is positive and one is negative, then yes, it'll always alternate back and forth between plus and minus. If they're both positive, then everything's positive. And if they're both negative, I don't know. You know, if they're both negative, you could factor the negative one out and then just raise it to whatever the power is. So I've never done one where they're both negative. It just seems like a waste of time. But if one of them is positive and one of them is negative, it will always oscillate back and forth. Yes. Yes, ma'am.
What is the point of writing 14641 with the equation?
The 14641 was these numbers. That's this part of the equation. It's right there.
Well, yeah, I understand the top. I just don't understand the next step of why you would write.
You want to know why I wrote this line?
No.
Why I wrote this line?
Yeah. With the 146.
Just to show you that this is 1, this is 4, this is 6, this is 4, this is 1. And to show you how I'm simplifying by hand. Could you go from here to here with a calculator? Sure. But I don't have a calculator in my hands. Next. It says find the coefficient of the term that actually has x to the fifth in it when you expand x plus 3 to the seventh. I'm going to write the binomial theorem for you. And then look here and see what letters you have. Oh, yes?
Do we need to memorize the binomial?
Yep, you sure do need to know the binomial theorem. Let's look what letters we have. We have A, we have B, and we have N. The only letter we don't have is R. We have A, we have B, we have N. A is X, B is 3, N is 7. So if you fill this bad boy out, if you fill this thing out, what you get is N, 7, choose R. A, which is X, please put your A and B in parentheses, raised to the N minus R, B to the R. This will generate all of the terms of this expansion. We are supposed to be looking for the one that has an x to the fifth in it. Please notice that all of my x's are right here. We need x to the 7 minus r to be equal to x to the fifth. That means 7 minus r is 5, so r is 2. What does that tell us? It tells us we're looking at term 3 of the expansion, and if we plug in 2 here, here, and here, we will see what term 3 is in that expansion. Term R2 plus 1, so term 3, is 7 choose 2, x to the fifth, 3 to the 2. Now look, I don't feel like writing out the 7th row of Pascal's triangle, so I'm going to grab a handy dandy calculator. You know that the calculator can't deal with variables, so I'm going to write x to the fifth at the back. But what I am going to do is I'm going to figure out what these two things multiply to get me. So we do it like this. You can either press math and scroll over to probability, and you see it's number 3. Or you could press alpha, window, 8. It doesn't matter. 7 choose 2 times, I don't even have to think here, 3 squared. I just asked the calculator to multiply all those numbers for me, which, London, kind of answers your question. Why was I even doing this? I was showing you how to do it by hand. Because you always could have just done this. And then hit equals, and you get the number 189. The question says, what is wrong with this blue pen today? The question says, what is the coefficient of the term that has x to the fifth? The answer is 189. That is the coefficient of x to the fifth in the expansion. Yes, sir.
When writing the binomial expansion
Mhm.
equation, is R and M, are those subscript?
R and N.
T.
T sub R, that's R plus 1.
Okay.
T sub R plus 1. And that's why we knew it was T sub 3, because we found out that R was 2. So we did T sub 2 plus 1. So the third term. Yes, ma'am? The 189 is 7 choose 2 times 9. Yes. I think 7 choose 2 is 21. Yeah. This is 21 times 9. This number must be 21. So the binomial coefficient is 21. But what's the coefficient of the term that has x to the fifth? 189. The binomial coefficient there is 21. 7 choose 2. But the coefficient of the term is 189. Okay? Other questions about that? Nuh-uh, he says. Okay. This question says, if you have the expansion, in the expansion of 6 choose 2, what coefficient does this represent on Pascal's triangle? And to explain. So I'm going to tell you which position it is. So if you have 6 choose 2, what is R? It's 2. So this is what this says. Row 6, this is row 6, and R equals 2. Since our formula is T sub R plus 1, we're looking at term 3. That's what that represents. Well, coefficient of term 3. I forgot to write the words coefficient of. There. It's the coefficient of term 3 in row 6. That's what that means. And that's all the explanation you need. That's it. And just in case you weren't sure, I could flip the paper over and go back to row 6. Oh, look, there it is. 6 choose 2. It's the third term in this row. Because it's always T sub R plus 1. Isn't that neat? So why do things like this? Well, in case I wanted to do crazy things like this. And then I said something like, find the term that has x to the fifth in it, or some bull stuff like that. Now we could do that. And we will do that when we come back from our nice long hurricane break. Thanks, nerds. Appreciate it.